I stumbled across this problem online, and I think it's going to lead to a pretty interesting discussion. So the question for this video is, can we give a proof that the cosine of 1 degree is an irrational number? And I think it's going to be an interesting discussion because this is going to lead to the rediscovery or the motivation behind some mathematical objects called the Chebyshev Polynomials. Or at least my method of solving this problem is going to introduce some objects called the Chebyshev polynomials. Of course, like many things in math, there are many ways to solve a given problem, but we're going to rediscover the motivation behind these mathematical objects. Now, this proposition that the cosine of 1 degree is irrational is certainly pretty reasonable if you just do some computation. If you plug into your calculator the cosine of 1 degree, or in radian form, which I'll use from now on, this is equal to the cosine of pi over 180. Since this angle is pretty close to 0, the value of this is approximately 1, but if you load it into your calculator, it's a pretty wild number. And it's certainly not obvious that it should be a rational number. It's not obvious that there are any repeats in the number, and the digits look pretty random. So this proposition that this is irrational is certainly plausible. I was thinking about this problem. The first thing I considered was just the definition of the cosine function from a computational point of view. How do we calculate cosine? Well, we usually have to make reference to its Taylor series. So I just started considering the Taylor series. And I figured that you can just plug in pi over 180 and maybe something nice would pop out at you. So I just plug in pi over 180, and I figured there would be some nice factorization or some nice contradiction that I could arrive at. Perhaps contradiction might be showing that pi is a rational number, but I couldn't really find anything going with this method. Maybe you can find something I'm not seeing. But the next thing I considered was just what we know in a bare bones sense about the cosine function. And what I'm going to draw here is just the unit circle in the first quadrant. So we know a few nice values of the cosine function exactly in the first quadrant. And by extension, all the other quadrants. We know that just starting from the smallest angle, cosine of 0 is going to be 1. Cosine of 30 degrees, or pi over 6, is going to be root 3 over 2. The cosine of pi over 4 is going to be root 2 over 2. The cosine of pi over 3, or 60 degrees, is going to be 1/2. And finally, the cosine of pi over 2 is going to be 0. So nothing really radical here. But the thing I started thinking about was, let's say we know for a fact that the cosine of pi over 4 is, another way to write this is 1 over root 2. We know that this number is irrational. And that's pretty certain, that the cosine of 45 degrees is 1 over root 2. We know that's irrational. And what I started thinking about was the angle that I'm interested in is a very small angle right here. Let's say that's the 1 degree angle. That 45 degree angle, or pi over 4, is obviously bigger, and it's 45 times bigger. So what I started thinking about was, if we know the cosine of some angle, if we know that's irrational, can I make any conclusions about divisions of that angle? For example, if I know that the cosine of some angle x, actually let me not use x, let me say theta, is irrational, can I make any conclusions about the angle theta over 2 or theta over 3? That is, if I know the cosine of pi over 4 is 1 over root 2, which is certainly irrational, can I make any conclusions about theta over 2, which would be pi over 8, or theta over 3, which would be cosine of pi over 12? Is there any theorem concerning that I could make a conclusion based upon the irrationality of cosine of some angle theta. And I claim the answer to that is yes. And by extension, what you can end up showing is that since this 1 degree angle is 45 times less, eventually what I have to make a statement about is if the cosine of theta, if that's irrational, does that imply that the cosine of theta over 45 is irrational? And it turns out that the answer to this is yes, and that's what I'm going to show in this video. And the reason for this has to do with the fact that 45 can be written as 9 times 5, or 3 squared times 5. So what this means is that if I can demonstrate that the irrationality of cosine pi implies the irrationality of cosine theta over 3, and also that the cosine of some angle theta implies the irrationality of theta over 5, I can just compose these theorems. I can apply this theorem twice and apply this theorem once to show that the cosine of theta implies that the cosine of theta over 45 is irrational. So this is what I'm going to essentially talk about in this video. Is I'm going to try to make some statements about how the cosine of theta being irrational implies that the cosine of theta over 2 is irrational. Also that the cosine of theta over 3 is irrational, cosine of theta over 5 is irrational, and so on. And that's what's going to lead to the Chebyshev polynomials. You can probably observe that I'm going to have to make some statements about the cosine of theta over 3 and some statements about the cosine of theta over 5 with regards to being irrational. But first, to give you a sort of intuition about what's going on here, I'd like to consider the cosine of theta over 2. That is, we're going to just consider some fundamental trigonometry. We're going to consider the double, or equivalently the half angle formulas. And this is what's going to get us to polynomial expressions, namely the Chebyshev polynomials. What I'm going to do is rederive the double angle formula for cosine. So let's say we had cosine of 2 theta, and I want to express a cosine of 2 theta in terms of theta, just theta. So what that means is that if I know cosine theta, there's some way of calculating cosine of the double angle. Or equivalently, if I know the larger angle, the double angle, if I know cosine of 2 theta, there's some way of back calculating cosine theta. So if I just use the addition rule for cosine, let me just write cosine 2 theta as theta plus theta. And you probably know through the cosine addition formula that this is going to be equal to cosine theta times cosine theta minus sine theta times sine theta. And this is how you get to that expression, that the cosine of 2 theta is equal to cosine squared theta minus sine squared theta. That's equal to cosine 2 theta. And if I want to write this completely in terms of cosine theta, I also use that Pythagorean identity that the sine squared of theta plus cosine squared of theta is equal to 1, because this implies that the sine squared of theta is equal to 1 minus cosine theta. So I'm going to take that sine squared, make the substitution right there. And what I get is, just going to copy down that cosine squared theta, and I get minus 1 plus, just got to negate that right there, plus cosine squared theta. And just combining these two terms, I get that the cosine of 2 theta is equal to 2 times cosine squared theta minus 1. So this is the double angle formula for cosine. And if you solve for cosine theta, then you just call that the half angle formula. What is this telling us right here? It says that if I know computationally, if I know cosine theta, knowledge about cosine theta implies knowledge about cosine 2 theta. Just to give these different symbols, let me make the definition that x is going to be equal to cosine theta. So we start with some x value. So I'm going to make that substitution there, that x is equal to cosine theta. So what I am getting is 2x squared minus 1 equals this side here. And I'm going to just change some symbols around. I'm going to let y be equal to cosine of 2 theta. So that's going to be equal to y. So you can see here that this cosine 2 theta can be expressed in terms of a polynomial expression in x, where x is equal to cosine theta. And equivalently, suppose I gave you, let's say you're given the y value, that is, you're given the cosine of the bigger angle, and the question is, can you find the x value, can you find the half angle? The answer to that question would be yes, because if you just rearrange this equation, we get that 2x squared minus 1 minus y is equal to 0. And this question is the same thing as solving a quadratic, which can always be done. You can always solve the quadratic equation. So what we've just done here is we've taken this cosine of 2 theta and we've expressed it as a degree 2 polynomial. And as it turns out, this special polynomial that we've just derived, 2x squared, let me copy that down, 2x squared minus 1, is called the second Chebyshev polynomial. And the Chebyshev polynomials are written with a t, and then the subscript is going to denote whatever degree it is. So for the case of cosine 2 theta, that's going to be written as the second Chebyshev polynomial. To be precise, these are called the Chebyshev polynomials of the first kind. That is, of the first kind. And we've just found what t sub 2 is. And what we're going to eventually do is find what t sub 3 is going to be. This is going to be some degree 3 polynomial, and it's going to be related to, expectedly, cosine of 3 theta. And we're also going to find what t4 and t5 are going to be. And what these are doing conceptually is they're relating cosine of some integer multiple of theta, let me call it n times theta, in terms of just plain old cosine theta. So this is conceptually what the Chebyshev polynomials are doing. And what we've just derived here for the double angle formula of cosine is the second Chebyshev polynomial of the first kind. Let me just copy down what we have so far. We saw that the cosine of 2 theta is equal to 2 times cosine squared of theta minus 1, which, using that notation I adopted, we converted this to the polynomial expression y is equal to 2x squared minus 1. And this is the second Chebyshev polynomial of the first kind. So what does this mean geometrically? Let's say I draw out this unit circle one more time, or at least some of it. Here's the upper division of the unit circle. Let's say I sweep out some angle, let's say that angle, and I'm going to let this angle be 2 theta, and then I'm going to bisect the angle so that I get the smaller angle here. And remember what cosine means. I just project this point down to the x-axis, and using my notation, this would be the y value, and then projecting this notation down to this point down to the x-axis, using the notation, this would be equal to the value x. And the x and y values are related by the following equation. Y is equal to 2x squared minus 1. So what that means is if I give you the value of x, you can calculate y for me. That's an easy computation. And if I give you y, you can solve for x. since you can just solve for x algebraically here, or you can use the quadratic formula or whatever. So this is pretty nice. That knowledge, as I said before, knowledge of x implies knowledge of y, and knowledge of y implies knowledge of x. But let me show you why this is going to be useful in terms of proving why the irrationality of y implies the irrationality of x. Why the irrationality of the cosine of the bigger angle implies the irrationality of the cosine of the smaller angle. So that's the first lemma that I'm going to prove first, that the cosine of some bigger angle theta being irrational. So just to write this out, if this value, cosine theta, is irrational, that implies that the half angle, theta over 2, cosine of theta over 2, is irrational. So notice here that I'm using, instead of 2 theta and theta, I'm just using theta and theta over 2. But the relationship is the same. This angle here is going to be the bigger one, and it's going to be twice as big as this angle. So what I'm going to do is I'm going to make the assumption that cosine theta is going to be irrational, and I'm going to do a proof by contradiction. So what I'm going to do is assume that cosine theta is irrational, and I'm going to assume or suppose the opposite of this conclusion, that cosine theta over 2 is rational. And I'm going to show how this assumption here, or this supposition that cosine theta over 2 is rational, contradicts this assumption. So using my notation before, y is going to be equal to the larger angle, or the cosine of the larger angle. Y is equal to cosine theta. X is going to be equal to cosine theta over 2. And by our supposition, this can be written as a ratio of two integers, let's say a over b. And I had that equation, the Chebyshev polynomial, y is equal to 2x squared minus 1. Now I'm supposing that x can be written as a over b, so I'm going to make that substitution to x here. We get 2 times a over b all squared minus 1 is equal to y, which is equal to 2 times a squared over b squared minus 1. And writing 1 not as 1 but b squared over b squared, which is equal to 1. This is equal to 2a squared minus b squared all over b squared. But notice what this is here. This is a rational number. So this is in contradiction to our other assumption that cosine of the bigger angle was irrational. So this is a contradiction here, because this is a rational number. So that means that the opposite of our supposition is true. It's not rational. So that means that the cosine of theta over 2 is irrational. And that concludes the proof of this lemma. Here are some example statements that I can now conclude with certainty from that proof. We know that the cosine of pi over 4 was equal to 1 over root 2. And we know that this is an irrational number. 1 over root 2 is irrational. So by the theorem, this angle produces an irrational number. The cosine of this angle produces an irrational number. So the cosine of the half angle is also guaranteed to be irrational. And I could keep recursively applying the theorem. This also guarantees that the cosine of pi over 16 is irrational. So you can see that this theorem is recursively implying a bunch of other statements too. That if the cosine of theta is irrational, that implies that the cosine of theta over 2 is irrational, cosine of theta over 4 is irrational, cosine of theta over 8 is irrational, cosine of theta over 16 is irrational, and so on. Each one of these statements gets linked to one another because I demonstrated this first statement. So this is pretty interesting already, that if I have some angle theta and it divided by some power of 2, then I'm guaranteed that the cosine of that new angle is going to give me another irrational number. You can see that calculating what T2 was allowed me to make those statements about if the cosine of theta is irrational, then that implies that the cosine of theta over 2 is irrational. But eventually what I want to work my way up to doing is making a statement that looks like this. The cosine of theta being irrational implies that the cosine of theta over 45 was irrational. Because I want to make my way of showing that the cosine of 45 degrees being irrational implied that the cosine of 1 degree was irrational. But as we observed before, this theta over 45 can also be written as theta over 3 squared times 5, since this is just 9 times 5. So what this means is that I'm going to eventually have to work my way up to finding what T3 and T5 are going to be, or just showing that these are going to be well-defined things in terms of cosine theta. And then when I show those, once I give you what those things are, I can apply that logic for T3 twice to demonstrate that if the cosine of theta is irrational, that the cosine of theta over 3 squared, which is equal to cosine of theta over 9, is irrational. And it's 3 squared because I just applied this theorem twice. And then I'm going to apply this theorem eventually. And that's going to get me to the conclusion that this is irrational, that theta over 45 is going to be irrational, or the cosine of theta over 45 is going to be irrational. Since I've already found T2, let me now work my way up to showing you what T3 is, the third Chebyshev polynomial of the first kind. And this is going to rely upon the cosine addition rule, just as T2 did. So I'm going to consider cosine 3 theta, and I'm going to rewrite this as cosine 2 theta plus theta. And then I apply the cosine addition rule. So I'm going to have cosine 2 theta times cosine theta minus sine 2 theta times sine theta. And then I'll just remind you that we have the double angle formula for sine, which said that sine of 2 theta is equal to 2 times sine theta cosine theta. So remember what we want to do. We want to express cosine of some multiple of theta in terms of cosine thetas only. And luckily, I just found what cosine 2 theta was. That was T2. I have a cosine theta there, which is no problem. But then I'm going to have to make some substitutions here. So let's start substituting. I have that the cosine of 3 theta is equal to cosine 2 theta, which, as we said before, that was at 2x squared minus 1, which is 2 cosine squared theta minus 1 times an additional cosine theta. And then on the right here, I'm going to make that substitution for sine 2 theta right here. So I'm going to have 2 sine theta times cosine theta, but it's being multiplied by an additional sine theta. So that sine theta right there is going to be sine squared theta. So let me write that down. 2 sine squared theta times cosine theta. And then just to remind you, I have that Pythagorean identity between sine squared and cosine squared. And that said that sine squared theta is equal to 1 minus cosine squared theta. So I'm also going to substitute that. So let me just copy down what I have here for that first term there. And then I make that substitution, 1 minus cosine squared theta, another cosine theta there. And then I just start distributing. On the left here, I'm going to distribute an extra cosine theta factor to these two terms. I have 2 times cosine cubed theta minus cosine theta. And then on the right here, what do I have? I have minus 2 times 1 times cosine theta, which is going to be minus 2 cosine theta. And I have minus 2 times minus cosine squared times an additional cosine, so it's going to give me plus 2 cosine cubed of theta. And then I just combine all the like degrees. I have the 2/3 degree terms here, there and there. So let's look at combined to 4 cosine cubed theta. And I have 2 first degrees here, so it's going to be minus 3 cosine theta. And this is still equal to cosine 3 theta. So you can see what I have here. I have an expression for cosine of 3 theta in terms of cosine theta only. And just to convert to my old notation, the bigger angle, the cosine of the bigger angle is going to be called y, and the smaller angle, the cosine theta, is going to be called x. So the polynomial expression can be written as 4x cubed minus 3x. And this is going to be T3, the third Chebyshev polynomial. It's going to be 4x cubed minus 3x. Let's keep track of what we have so far. We saw that T2 was equal to 2x squared minus 1. Then we derived T3, which we saw was 4x cubed minus 3x. And by the way, we can also write down T1 and T0. T0 corresponds to cosine of 0 times theta, which is, of course, is equal to cosine 0, which is equal to 1. So T0 is just 1. And cosine theta of 1 times theta, there's not much we can do with that. So cosine theta just gets the name x. And so we have the first, really 4 Chebyshev polynomials, T0, T1, T2, and T3. So let's continue on and derive T4. So T4 is not going to be too difficult because we can reduce it to a half angle formula for 4 theta. That becomes 2 theta. And then we can apply our knowledge of T2. So let me show you what that looks like. So again, we start with cosine 4 theta. But since we know what T2 is, we can interpret this in a half angle sense. We can say that this is equal to 2 times cosine of 2 theta all squared minus 1. That is, I just let x be equal to cosine 2x instead of cosine x. But you can see here, this angle is half of that angle, or that angle is double that angle. And I apply T2 again. I change the argument to theta instead of 2 theta. So for cosine squared 2 theta, I just make that substitution into itself. So I'm going to have cosine of something squared minus 1. Now what's cosine 2 theta? That's going to be 2 cosine squared of just theta minus 1. So you can see I've taken T2 and I've substituted it into itself to arrive at this expression for T4. It's going to be T4 over here. And then this is just algebra from here. So I'm going to have 2, and I'm going to square this thing. So I'm going to have 4 cosine to the 4th theta. Then the middle term is going to be minus 4 cosine squared theta. And then the final term is going to be plus 1, close parentheses, then that minus 1 out there. Then I just distribute the 2. So I'm going to have the 4th degree term is going to be 8 cosine to the 4th theta. That second degree is going to be also an 8 for the leading coefficient. So 8 cosine squared theta. Then I'm going to have 2 times 1, which is 2, and then minus 1, which is going to be plus 1. And then just to incorporate the notation here, I can rewrite this as 8 times x to the 4th minus 8x squared plus 1. and that's going to be t4. So at this point, let me convince you that all this stuff is working with a numerical example. Let's take the case of cosine of pi. And we know that's equal to -1. So graphically, what's going on? Let's say I have that upper arc of the unit circle. This is going to be cosine pi here. That's going to be -1. And then I'm going to consider cutting this angle into 4 parts. So I'm going to apply t4. So I'm going to cut into 4 parts. So that's 2 parts and 4 parts. So that means that this thing here is going to be my x, and that's going to be my y. And we know that the y's and x are related by the following equation. Y is equal to 8x to the 4th minus 8x squared plus 1. In this case, y is going to be equal to -1. But we already know what cosine of theta over 4 is. That's one of those easy ones. So cosine theta over 4, that's cosine of 45 degrees. That's going to be 1 over root 2. So that should be my x value. That should be my y value. So let's compute this just to make sure it works. So I claim that if you substitute x equals 1 over root 2 into this polynomial expression, you should get out on the left-hand side -1. So let's verify that. We have 8 times x to the 4th, so I'm going to have 1 over root 2 to the 4th power minus 8x squared. This will be 1 over root 2 squared plus 1. So here I have 8 times, I have 1 over root 2 to the 4th, so I can square that twice, so it's going to end up being 4. So I'm going to get 8 divided by 4 minus 8 times 1 over root 2 squared, which is going to be just 2, plus 1. 8 divided by 4 is 2, minus 8 divided by 2, which is 4, then plus 1. So I get -2 plus 1, which is indeed -1. So we can see that these Chebyshev polynomials are actually doing something. Here's what we have now in terms of the Chebyshev polynomials. And I'd like to tell you at this point about the recurrence relation so that we can very quickly calculate the next polynomials. And the recurrence relation is the following. That t sub n, where n is some number, is going to be equal to 2 times x times the polynomial that came just before it, which is n minus 1, minus the polynomial that came 2 before it, which is n minus 2. And what this means is that now I want to calculate what t5 is going to be. And by this formula, I claim it's equal to 2 times 2x times t of the one that came just before it, which is t4, minus the one that came 2 before it, which is going to be t3. So that means if this formula is true, that t5 should be equal to 2x times t4, and we know what t4 is. That's 8x to the 4th minus 8x squared plus 1, minus t3, which is going to be minus 4x cubed plus 3x. And now just looking at the degrees, we're going to have 16x to the 5th minus 16x cubed plus 2x. Then just copying that down, 4x cubed plus 3x. And just simplifying, the only thing we can really do is simplify the degree 3 and degree 1 terms. So it's going to give us 16x to the 5th minus 20x to the 3rd plus 5x. And that's going to be t5. So let me copy that down up here, 16x to the 5th minus 20x cubed plus 5x. And to put this all in terms of the cosines again, what this means is that if I have cosine of pi, again, that's equal to -1. And if I calculate what cosine 5 our cosine of pi over 5 is going to be, and let me see if I can calculate that right here. This is going to be about 0.809. So what does this mean? Since this angle is 5 times less than this one, or you can say that this one is 5 times greater, that means that the following polynomial equation has to be satisfied. Again, let me call the cosine of the bigger angle y and the cosine of the smaller angle x, that this equation must be satisfied. Y is equal to 16 x to the 5th minus 20 x cubed plus 5x. So I encourage you to check this, that minus 1 is approximately equal to 16.809 to the 5th power minus 20 times 0.809 to the 3rd power plus 5 times 0.809. At this point, I think we have enough machinery to demonstrate our initial proof, which was we want to say that the cosine of pi over 180 is irrational. And let me do this by proving two lemmas. Let me call them lemma 1 and lemma 2. And lemma 1 is going to say that if cosine theta is irrational, that implies that cosine of theta over 3 is irrational. And to do this, just like I demonstrated the related claim for theta over 2, for cosine of theta over 2 using the second Chebyshev polynomial, I'm going to use the third Chebyshev polynomial to demonstrate this one. And again, I'm going to do this by contradiction. I'm going to assume that cosine theta is irrational. That's just a premise of the lemma. And I'm going to assume the opposite of the conclusion. So I'm going to assume that the cosine of theta over 3 is rational. It can be written in the form a over b, where a and b are some integers. And we said that T3 was the following polynomial expression, y equals 4x cubed minus 3x. And now this is going to be equal to x, so let me make that substitution into this equation. So for x, I get a over b all cubed, so it's going to be a cubed over b cubed minus 3a over b. And hopefully you can see just by combining the two, the common denominator is going to be b cubed, that these two fractions are going to combine to, let's see, I'm going to make that b cubed, so I'm going to have to multiply by b squared, or yeah, b squared on top, so minus 3ab squared. And this is equal to y, and this thing right here is a rational number. And that contradicts our assumption that the cosine of theta, or y, that was y, was irrational. So we've arrived at a contradiction. So that means that if cosine theta is irrational, then cosine of theta over 3 must be irrational. And let me show you numerically how this all cashes out. We know that the cosine of theta, cosine of pi over 4, was equal to 1 over root 2, which was irrational. So it satisfies the if statement of this lemma. So by this lemma, that implies that the cosine of pi over this over 3, which is going to be pi over 12, is irrational. Whatever it is, it's irrational. That's what this lemma says. So now, let me prove lemma number 2, which is going to say something very similar. It's going to say that if cosine theta is irrational, then cosine of theta over 5 is irrational. And the mechanics of this proof are going to be exactly the same. I'm going to assume that cosine of theta over 5, which I'm going to call x, can be written in the form a over b. And then you use the fifth Chebyshev polynomial, which is going to be y equals, let me see what I have here, 16 x to the 5th minus 20 x cubed plus 5x. And what you're going to do is you're going to substitute this expression for x into those three locations there. And if you work out the algebra, you're going to find that y is going to be rational, that y is going to have to be some rational number. It's going to look something like this. You're going to get some complicated expression in the numerator, and you're going to get something like b to the fifth in the denominator. But no matter how complicated it is, it's still going to be a rational number, which gives you that contradiction, which would prove this lemma. And again, just to show you how this cashes out, I have that the cosine of pi over 4 is irrational. And if this lemma is true, that implies that cosine of pi over 20, let's just divide this angle by 5, that the cosine of this also has to be irrational. And finally, let me show you how those two lemmas get us to our conclusion that the cosine of pi over 180, which is equal to the cosine of 1 degree, is irrational. And again, I start with my knowledge that the cosine of pi over 4, which is 1 over the square root of 2, this is irrational. And now I'm going to use lemma 1, which was that statement about the relation between theta and theta over 3. So I'm going to apply that lemma to cosine of pi over 4. So lemma 1 implies that the cosine of pi over 4 being irrational implies that the cosine of pi over 12 is irrational. So that's true by lemma 1. I'll represent that as L sub 1. So we now know that this is irrational. So I'm going to apply lemma 1 more time. So the cosine of pi over 12 being irrational implies that the cosine of pi over 36 is also irrational. And now, for my final trick, I use lemma 2, which gave me the relation between theta and theta over 5. And now I know that cosine of pi over 36 is irrational. So I apply lemma 2. I have cosine of pi over 36. And that gets me to the conclusion that the cosine of pi over 180 is irrational, just because I divide this by 5. 36 times 5 is just 180. And that concludes the proof that this number is not rational. And I think that'll pretty much wrap up this video. Just like to make a few last-minute comments about the logic behind these theorems. Notice that we had theorems that looked like the following. That if cosine of theta is irrational, that implies that cosine of theta over 3 is irrational. Or theta over something is irrational. Now notice that if I take the contrapositive of this statement, that creates a new logical statement where the if statement is the negation of this statement, and then the then statement is the negation of this statement. So the truth equivalent statement of this is that if cosine of theta is rational, then that implies that the cosine of 3 theta has also got to be rational. And I encourage you to do some computation with this. Pick a theta such that cosine theta is rational, and compute cosine 3 theta, and you'll also observe that that value is rational if cosine theta is rational. And furthermore, these Chebyshev polynomials have some very nice applications in data analysis. And they come into the context of what's called the Chebyshev filter. And in the realm of at least neuroscience, because that's the only way I can really talk about with any authority, we definitely use this all the time to filter out certain frequencies, in addition to other things like the Butterworth filter and a bunch of other filters, which are generally used to filter out different frequencies. And I think that'll do it for this video. Hopefully you've enjoyed this discussion of the Chebyshev polynomials. And if you enjoyed this video, feel free to subscribe to my channel and stay tuned for more videos. Thanks again for watching.